it is time again for Astronomy Daily Live. Hey, everybody. Hope everybody's doing well out there in the live world. And hi to everyone who is coming in later that's not able to see the live stream. But yeah, I think this is good either way. Either way. So come on in, join the virtual circle of friends who get together every single day at 2 hours UTC and turn off the TV, forget about the news. Let's think and talk about the universe for an hour or so. Hope everybody's doing well out there. All is well here. Another relatively quiet weekend. I've been playing a little bit um, playing a little bit more with some data from the planetary data system. I went over to the Maven um, um, archive. They had just released a data set like a month ago or so, and one of the instruments on there is also a fluxgate magnetometer. And so it's like, okay, well, I'll take a look at that. And so um, if you haven't yet, I posted a little video uh, uh, showing a little bit of the data or so. It's yeah, it's pretty complicated. It's uh, yeah, pretty interesting stuff. So other than that, yeah, it's been sort of a quiet weekend. Hey, Atawa Hinta, nice to see you in the chat. You made it. You made it. Cheers. So yeah, all is well here. Trying to think if there's anything interesting astronomical going on. I don't think so. I think in the past 24 hours or so, um, the moon got relatively close to Jupiter from our point of view, but otherwise, just sort of the usual kind of excitement, right? Usual kind of excitement. Um, yeah, yeah. Ata, or is it Eta? Atawa Hinta. That sort of flows though. That's kind of nice. So there's another person um, who comes in here. Their name is Heptacular Raptor, and that sort of flows flows too. So yeah, I don't mind the complex names. I think they're great, incredibly inventive, and they're your own, right? Right. These are our chosen names rather than our given names, and yeah, I sort of appreciate that. So yeah, yeah. So yeah, hope everything is well with you over there, Ata. So okay. Oh, cool. Very, very cool. So one who can see forever. Wow, uh, that's quite a responsibility. So, all right. Well, hope everybody's doing well out there. Uh, oh, very cool. Very, very cool. I um, uh, so I went over what I usually try to do. Um, archive.org gets updated around 1 hour UTC every weekday. So at at a little bit after 1 hour UTC, I went over there, and I noticed that the yes, indeed, the latest and greatest bleeding edge um, papers, not only all the astronomical ones, but they have computer science, they have all kinds of other physics, they have mathematics. I mean, you can just get totally lost in all of that. So I mean, um, as if uh, um, you don't have enough to do already. Um, Ata, in terms of looking at the PDS. You can also get completely lost in archive.org, right? And that's AARXIV.org if you don't already know. So, um, uh, yeah. Um, I 100 million years isn't really all that long ago. Not really astronomically speaking. Um, it's well, of course, it's impossible to know for certainty. There are those who think that in much shorter time scales, things were very different. But if you sort of go um, go with the consensus right now, 100 million years um, uh, um, isn't really all that long. Um, if you go with the consensus model, right, then 100 million years ago, the moon probably didn't look all that much differently than what it did or does now. Um, yeah, the probably the patterning of the cratering and all of that is slightly different, but 100 million years really isn't all that long. So if you want to talk, you know, um, like 1 billion years, or 2 billion years, then we're starting to get into the time scales where you can sort of see some big changes if you assume um, sort of the standard model, which is just a model, right, based on current observations, right, which we really, I mean, we really haven't been uh, making observations for really all that long. So um, to be able to extrapolate backwards is I don't know. That's a tough one. That's a tough one. The models say things, but who knows? Who knows? But I think that Uncle Bill has a great suggestion there. Yeah, yeah. Um, and that's you know if you have astigmatism, then a telescope, looking through a scope, isn't going to help that much. Isn't going to help that much, but at least you'll be able to focus, right? You just um, move the focuser around. Yeah, sure, for sure. Let's see. All right, cool. I am running live. Yay, yay. But anyway, so I was over on. I don't know how I got off. Oh yeah, you were asking me about the moon. It's like, why was I talking about the moon? I don't know. Um, so yeah, I was over on archive.org, and I always find at least a couple sort of uh, you know just from the titles, it's sort of like, huh, that's kind of interesting. That's kind of, you know, never heard of that. So what I thought I'd do tonight is just do a little bit of exploring. And I was all ready to tweet. I had it all set up, and I didn't do it, but I'm going to do it now. There. It's all I have to do is press the button. It's all I have to do is press. I've got it all typed out. I've got the graphic. I've got everything done, and I get started here, and it's like focused here, right? It's like, So thank you, Uncle Bill, for keeping me on my toes, keeping me on my toes. So yeah, so I was over on archive.org and found, well, we're just going to be doing a little bit of exploring tonight together, learning some new things. Um, because, um, as I said, this live stream really isn't about communication in terms of me, teaching you things, any kind of um, um, educating or anything like that. Those those things will happen, right? But the primary thing here is is that we are just getting together and thinking and talking astronomy, and I mean, we will learn things, right? Um, because that's what the process of science is. The process of being very curious, very skeptical, and very open-minded. And I I sort of hold those three um, um, elements together when I dive into things, and that's sort of what this live stream is all about. Is you know getting together. It's fun. It's casual. It's really loose. There's no hurry. There's no rush at all. Um, uh, we can skim along really shallowly. We can dive really deep. You know, pretty much wherever we want to go, right? Because it's all of us. It's not really just me. I mean, I've got the porch, right? And you're all coming to my porch, but that's it. As far as discussions go and all of that, um, I mean, I can talk about anything, right? More than happy to. Uh, so yeah. Anyway, so I was looking at archive.org, and I'm going to share my screen here. Share my screen. Share the screen. We go to infinity. And we're going to come over here and we'll go over to my Discord server. If you haven't joined the Discord server yet and want to, please do so. There's in fact, Uncle Bill, tonight I will send the invite out because I know how to do that. I'm going to do it right now. I'm going to put it in the chat. Huzzah. There we go. Yeah, there uh um Atta, I see a lot of sort of science oriented podcasts it's they um they sort of giggle and laugh at things that aren't sort of the standard normal way of thinking about things. The consensus view. Anything that isn't consensus, they sort of, poo-poo and laugh at. And my attitude is that, look, there are jewels in all of those things, right? I mean everything that we think is true today, at some point in the past was absolutely ridiculous, right? Um, so I I don't like to poo-poo anything at all. I like to take a good hard look at it, right? And see if it measures up. And if it doesn't, then I just ignore it, right? I mean, it's like, well, it's just you know not worth the time, or the effort even to criticize it, right? Because it's like, I don't care. Anyway, so this is the one that I thought was kind of interesting, because I'd never heard of this before. Um, there's this object called um, the quintuplet cluster, and I'd never heard of that at all. So, and that's that. Um, like I always say, all of these papers are, um, at least can be viewed as sort of jumping off points to learn stuff, right? Um, um, uh, okay, all right. Well, um, um, Uncle Bill, if you think that we need to be doing that a little bit more, then let's do it a little bit more. I'm I'm fine with that. So feel free. Uh, I'll try to remember too. So yeah, thanks. Um, yeah, and um, you know, I think that there's a place for um, everyone, right? There need to be those that um, poo-poo things and are critical of things and make fun of things, um, and all that. I think but that for me is sort of a red flag. Like, oh, well, I'm going to take a look at that then, because if the consensus is that this is wrong, then I'm going to take a look at it and decide for myself, right? Anyway, um, so I've never heard of this thing called the quintuplet cluster, and so this paper came up, and it says that the quintuplet is one of the most massive galactic clusters known. Um, and I'm like, wow, I've never heard of this, never heard of it, right? I mean, a galactic cluster is just a um, um, open cluster of stars. And it's like, why haven't I ever heard of this? Right. So that's why I think let's just take a dive into this. Um, and I'll sort of go through a few things. I mean, a lot of this is way over my head, a lot of it, right? But that's where a lot of learning can take place, right? I don't mind if things are over my head, as long as I can sort of, reach my arm up and, touch it a little bit, right? So I don't mind um, um, over the head, just as long as it isn't way over my head, so I can't even grab it, right? But if I can sort of, just even get a fingertip on it, and it's like, okay, well, I've got something. So, so uh, place date, data point. Yes, yes, that's absolutely true. And uh, a lot of times those those data points are removed, right? Because it's like, well, this isn't like all the other ones, so we're just going to ignore it, right? And that is definitely, not the thing um, to do unless you can show that data point is what it is because of some kind of systematic thing, right? I mean, if your instrumentation, caused the data value to be completely off, and you're aware of that, then you can throw it out, right? But otherwise, yeah, yeah, it's like the white crow, right? So yeah, yeah, yeah. There was something else I was going to say about that, but I lost it. I lost it. Um, yeah, absolutely. Oh, yeah, with this new um, data release from Gaia, there's a bunch of papers that are coming out now, um, uh, looking for these oddballs, right? Um, they're looking at these stars that are moving unusually fast, or they're moving in some kind of strange way. And yeah, those I mean, everything has value, right? I mean, you know those millions and millions and millions of stars that are all sort of behaving the way that we think they should, those have a lot of value too, right? An incredible amount of value. But these oddballs um, have, um, sort of an equal value, just sort of in a different way, right? So yeah, yeah, yeah. So anyway, I'm really curious to find out a little bit more about this quintuplet cluster. And I dove into the paper already here. Let me get rid of that, but I'm going to pull it up here. This is a long paper. This is like a 27-page paper, right? So I mean, and and again, I mean, I can't um, say this enough. It's the amount of work that goes into uh, you know just I mean, to write this kind of paper is a lot of work, right? But to get to this point where you can write a paper is just this massive amount of work, just this huge, huge, huge um, um, kind of work, and it just, I mean, my hat's off, to everyone that can do this, because it's just, I mean, I know very, very well how much work it is. And when I see, things like this, it's just mind blowing, absolutely mind blowing. So I think let's go over, let's Google the quintuplet. What do they call it? The quintuplet cluster. Quintuplet cluster. Now there's an asterisk there. What's the asterisk about? Based on observations made by ESO. Okay, okay, okay. So let's just see if there's anything. As I said, I've never heard of the quintuplet cluster. There's the Wikipedia page for it. Okay. There were some HST observations too, so I definitely want to go over and see. see those if we have time. So the quintuplet cluster is a dense cluster of massive young stars about 100 light years from the galactic center. Its name comes from the fact that it has 5 prominent infrared sources residing in it. Along with the Arches cluster, it is one of 2 in the immediate galactic center region. Okay, so because there's so much dust, right? There's so much stuff. I guess, yeah, it says that we're not able to see it in the optical wavelengths, but we can look at it in X-ray and radio and the infrared bands. So the quintuplet is less compact than the nearby Arches cluster, with fewer of the most massive and luminous stars, but it does have the distinction of hosting 2 of the extremely rare luminous blue variables, the Pistol star and QF362. Very cool. So it was identified in 1983 as a pair of infrared sources. Number 3 and 4, later referred to as the GCS, later resolved into 4 sources labeled 1 to 4 that together with GCS4 formed a compact quintuplet of unusually small, bright objects. They were assumed to be young, hot, luminous stars surrounded by dust shells and therefore extremely reddened. So in 1990, they found 15 sources. Original 5 stars were numbered Q1 through Q9. Additional sources Q5 and 6 identified as part of the same cluster. So they're still considered to be protostars reddened by surrounding dust. In 1994, several stars were identified as having broad helium emission lines in their spectra. So they were glowing in the helium. And some hydrogen. This this was completely unexpected for protostars. Shortly afterwards, 2 emission line stars were classified as Wolf-Rayet stars, and a third as a luminous blue variable that was thought to be one of the most luminous stars in the galaxy. A small number of red supergiants were identified. 1999, a study of 600 stars showed that this had a bunch more Wolf-Rayet stars than any known cluster, and a second luminous blue variable. Pretty interesting. Pretty interesting. So here's a list, at least according to Wikipedia, of the current members. Now this paper, right, this paper is going to update that for us. So this will kind of be a little bit interesting. So all the supergiants are classified as either 078 or 09B zeros. So O stars are sort of the brightest and the bluest and probably the most massive stars we know, at least some of them. some of the most massive ones. Early, which comprise the richest populations of stars in any stellar aggregate known. In parallel, we identify a smaller population of late O hypergiants and spectroscopically similar W989HA stars. I don't know. I don't know what those are. Um, yeah, there is so much. There is so much that I just don't know about these things. But that's why we're here, right? Um, so because they're, what they're saying here in their little conclusions, right, is that they really don't have a, a good grasp yet as to how much stuff is between us and this cluster of of stars. So they're saying that it's not, they're not really able to figure out the cluster age. Um, but nevertheless, we find an impressive coincidence between the properties of cluster members um, preceding the hydrogen-free Wolf-Rayet phase and the um, evolutionary predictions for a single non-rotating 60 solar mass star. So that's pretty massive. Yeah, that's pretty massive for sure. For sure. So yeah, they're thinking maybe 3 million years, which is very very young, very very young, just formed, just formed. So that's kind of an interesting thing, right? Because I mean they're close to the galactic center, um, uh, yet they're yeah. I mean I guess what that implies, right, is that the area around the galactic center is an area of very very intense and active star formation, right? Which I wasn't aware. I thought I don't know. I guess I didn't know what I thought, but yeah, I guess I just wasn't aware of that at all. Yes. So the hydrogen-free Wolf-Rayet stars must evolve um, from stars with an initial mass more than 60 solar masses, but it appears difficult to reconcile their observational properties with theoretical expectations. This is important since one would expect the most massive stars um, within the quintuplet to be um, to be actually supernovae at this time. Um, so since Wolf-Rayets represent a phase right before a supernova, their physical properties are crucial to understanding processes. Yeah, yeah, yeah. Very interesting. As such, the quintuplet provides unique observational constraints on the evolution and death of the most massive stars forming in the local high metallicity universe. Okay. So yeah, I had no idea that stars were being formed near the galactic center. Had no idea. I, I I guess I sort of thought maybe it's the other way around. That you'd have like very very old evolved stars there. But yeah, I guess if there's a lot of gas and dust, so yeah, don't know. Let's see. compact H2 regions. 8% of the dense. So what discrepancy are they talking about here? Okay, yeah. So isolated massive star points to dramatic recent and ongoing star formation within the CMZ, the central molecular zone, which is another term that I've never heard of. Never heard of that term before. However, despite containing some 80% of, wow, really? So the CMZ contains like 80% of the molecular gas within the galaxy. Wow. Um, and with the individual clouds apparently of sufficient mass and density to form clusters, the rate of star formation within the CMZ, um, they say, is depressed by at least one order of magnitude. Huh. Okay. So the reason for that discrepancy is unclear. Um, one might ask whether clusters and their constituent stars form in the same manner and have the same physical properties as their counterparts um, in the galactic disk. Important question, since circumnuclear starbursts are present in many external galaxies. Okay, all right. So they're seeing these kinds of things in other galaxies as well. Okay. Heavily blended source. Three groups successfully resolved the quintuplet into multiple stellar sources, um, extreme luminosity, prompt the question of whether the two clusters form via differential mechanisms or if secular evolution and or an interaction with an outside agent such as a tidal field um, led to the situation. Huh. Lots of questions. I mean, apparently this is just getting a lot of um, stellar evolution folks pretty excited. So that's a kind of an interesting problem. Results the possibility of a significant role for binary interaction in the evolution of the constituent stars of the quintuplet heralds a further observational opportunity. Current spectral analysis suggests that it hosts a rich and diverse population of post-main sequence objects, um, including comparatively rare objects such as luminous blue variables and hypergiants. Um, so those don't last very long. So the extreme mass loss, all the way up to the top, mass loss rates that characterize them are expected to profoundly influence the evolution of massive stars. Yeah, okay. Uh, if the cluster formation history may be adequately quantified and the properties of the putative binary population constrained, the quintuplet will serve as an excellent testbed for stellar evolution theory. Cool. Okay. So yeah, these are just observations, right? I mean, that's what the whole thing is that they're, you know, trying to get a census of what's going on, and so they've made a bunch of observations, right? Yeah, yeah. Well, you know, and um, Ata, for me, this is just fun, right? So I mean, I'm doing this anyway. I mean, this is usually how I spend my um, um, evenings when my brain's a little tired because I've been working all day long. Don't want to do much, so I'll just read papers, right? Um, or do some kind of astronomical thing. So it's like, oh, I'm just going to share it with everybody else. Let's see. So I'm sort of thinking. So here they're just talking about all the data that they acquired. You know, who, what, when, where, and why. And they're going to be starting to show some spectra here, which, you know, spectra tell us so much. Just an enormous amount of information is in these spectra. And yeah, this one's sort of tilted on its side, but they've identified a number of lines here, right? Here's helium 1, here's carbon 4, helium 1 and nitrogen 3 blended. Here's silicon 3, okay, magnesium 2, iron 2. That's kind of cool. These are just the names, the different stars, right? Silicon 4, magnesium 2 again. And of course, they're looking at these things um, in the infrared, right? So 2 micron. I think that's about the K band. Montage of spectra of selected O supergiant, B hypergiant, um, W stars, and luminous blue variable stars. So I don't know which one is which here. Is it pretty obvious? Oh, okay. So this bottom one is an LBV, right? And they're yeah, I mean, if you look at the differences between the spectra, there are subtle differences, right? I mean, this emission line here is much more prominent and narrower than this one. In fact, all these lines, right? Oh, and here's this line here in the blue variable that doesn't show up really. It shows up maybe a little bit here, a little bit here, but um, looks to me like these line widths are much more narrow, right? And that tells us something about the star. I don't remember exactly what. There's some complicated things going on here too, right? That maybe are showing up here, but these look a little more broad. Yeah, who knows? Who knows? Spectra are extremely complicated. Da, da, da. Right. Silicon 4, silicon 3, magnesium 2. Um, yeah, very, very cool. So again, this is just sort of um, describing how they acquired the data, how they calibrated, all of that. Yeah. Hey there, Bobby. I was over on Jill's live stream there for a few minutes or so, but I had to I had to bop off in order to get onto this. But I always like it when Gilles is on. He's an awesome guy. Let's see. So some pretty good spectra, right? But they're saying that the photometry isn't well. They only have it for um, 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 ground-based observations. Uh, with greater sensitivity and angular resolution than previous studies. Okay, so all right, yeah, they actually did look at this with HST because it's all they did have was ground based. So cool. We got some HST time and well, you know what? Let's go over and look at those. We can do that. I wonder if it will come up if we do quintuplet. I spell that right? Quintuplet. We'll look at the spectra too here. Ooh, no, huh? How are we gonna find these? How are we gonna find these? Maybe if we can, I think this might be the, so 7362. Let's see if that's the, let's clear the form. We'll do this and we'll do this and we'll do 7362 for the proposal ID. Let's see if it comes up that way. $19.99. That doesn't look right. Doesn't look right. I don't know what GO 7362 is. How can we find? Let's look for Figer, Figer. Can we search for PI name? PI last name. Here we go. Figer. There we go. There we go. And these are infrared wavelengths. Yeah, for sure. 1997. Okay, so far so good. I'll bet you that there's, I'm gonna fly through these, see if there's some like some observation logs. At all those spectra. As I said, they did a very thorough job. Um, this is just the list. I don't see an observing log anywhere. Yeah, don't see an observing log. So, well, let's just dive in here because I mean, this is using NICMOS, which is slash was the um, infrared camera, definitely 1997. So let's just take a look. Okay, well, we're definitely seeing stars, huh? 7364. Is that the one? I'm going to have to go all the way back up now. $73.64. Wow. That's 73.62. All right. Where's the Aryan deck? Oh, Aryan deck. Look at that. That is definitely galactic center. Yeah, definitely galactic center. We can look at a list of objects. Yeah, okay. So 1746 and negative 2849. Oh, yeah, we're there. We are there. Okay. So there's some infrared images of apparently what they're calling the quintuplet cluster near the galactic center. It's kind of cool. I'm almost wanting to grab these and make a color image out of them. See, it looks like these three were taken at different wavelengths. Oh man, I'm tempted. Oh, I'm very tempted. Very tempted. 1997, was that before or after the HST got fixed? Because I'm looking at those images and I'm saying, wow, I'm seeing a lot of garbage, right? Quite a bit of garbage around that. When was HST correction? I don't know if that's the right thing to search for or not. No. Scope servicing mission 1. So when was servicing mission 1? June 1990. Oh, yeah. They did that. The first. Okay, so 1993. Yeah, okay. Well, I'm not quite sure why they look that terrible, but I think what I'm going to do is I think I'm going to make a picture out of this. So let's make this one. Um, uh, this is the shortest wavelength. So let's make that blue. Let's make this one green and this one red. All right. So I'm just going to grab these as JPEGs. Ideally we would want to grab the actual raw data, but so let's call this one blue, right? Blue. And then let's do this one. And we're going to call this one green. GRN, that. And then let's grab this one and call it red. Nick Moss, I think, was like a 256 by 256 imager. So, you know, pretty small array, if I remember right. Was it 256 or 512? I don't remember exactly now. All right, so let's pull up GIMP and stack these pictures together and just sort of see if we can make an interesting color picture. Yeah, I sort of like these kinds of papers. You know, I mean, I'm I do lean towards the observational side of astronomy, but I mean, I like it all, uh, but um, I like the observational part because well, especially for, you know, like a live stream here, it's just it's a lot easier to deal with because, you know, I mean, you get into some pretty complicated things otherwise. So okay, let's load these as layers, and there they are. So red. Oh, that's the wrong one. Oh, am I in the wrong place? Oh yeah. Okay, let's go over here. Go here. Gotta go here. Gotta go here. Gotta go there. And let's pull those up to the top. There they are. So one. I'm gonna put you down just for a second. Hold on. Okay. So I should have these three should load. Chunk, 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 chunk. So now let me try to make this window a little smaller. So now I've got to turn this into an RGB image. So I go over here and change that to RGB. And then I go over here and I can just say screen and screen and screen. So now they're all sort of seen there. So let's make this one blue. Colors. And I'm trying to remember how we did this before. How did we do this before? There we go. So that's a pretty nice blue. And let's make this one green. Green. Oh, and we're going to invert these too. Let me do that first. Let me do that first. Let's invert all of these. So we have, you know, white stars and not black stars. Invert, invert, invert. Okay. So now let's make these blue. Colorize. Make it as blue as we can. That's a nice blue. And we'll make this one green. Colorize. let's see, where's the green? There's the green. We'll make that nice bright green. And we'll make this one red. And see what we get. It's a nice intense red. All right, so there we go. So it looks like a couple of these stars look pretty red, but a lot of them look pretty blue too. Kind of a noisy background. Okay. It's expected, right? I mean, you know, you're looking through a lot of stuff, right? And yeah, this I would just sort of call, you know, some kind of optical effect. Not well, hate to call it not real, but yeah, you know, lots of optics. That's a pretty good shot. That's a pretty cool shot of the quintuplet cluster. Pretty cool. Pretty cool. All right, well, what else does this thing say about this? I think probably one of the interesting things that I'm just sort of noticing, right, as I go through here, and sorry I'm scrolling through this so fast, but it's that table. Yeah, it's this table, right? So trying to see how many they identified, but this is a pretty large table now, right? I mean, when we looked at the Wikipedia page, right, there was only that many. Now there's all of these. So that's pretty cool. So they've identified a bunch more stars are, you know, part of that population. That's pretty cool. Wow. Some of these, I guess, it's sort of looking like, oh, maybe, maybe not. Hard to tell. Too faint, right? Magnitude is greater than 13th, which I guess is fainter than what they can really be sure of. So yeah, there's some questions there. That's all right. There's nothing wrong with having questions. Yeah, I'm thinking it's an optical effect too, for sure. For sure. Let me, you know, since I'm doing this, why don't I will post, I will, I'm going to merge the visible layers. Okay. And then I'm going to save this as a JPEG. And we'll call it, well, let's just call it quintuplet cluster. And I will send this over to the, I'll send this over to the Discord server right away. Let's see, where should we put it? Put it with science. We'll put it on the science channel. Let's see. So yeah, I had absolutely no idea about these things at all. So I'm always glad to learn, even if it's just a little bit about these kinds of things, right? And yeah, I mean, this is a big, massive paper, right? So we've barely scratched. Let's see. I'm going to do that. Let's see. Can I move it over? Yeah, I should be able to move it over here. There we go. Drag and drop. So the quintuplet. Quintuplet from HST data. Proposal. Always like to give credit if I can. So this is proposal number, or proposal ID 7364. 7364. There we go. Yay. Pretty cool. Pretty cool. But yeah, there's a lot more to this, and I'm just skimming over things, right? I mean, they've identified, look, I mean, it looks like they've identified various forms of carbon in here. Kind of pretty complicated little spectra too, right? You've got these funny little spikes here that are are there in this star and not there in that star. Pretty amazing. What else we got here? So more carbon, more helium. Carbon, helium. And these are all, different stars. They've plotted these so we can sort of see, the individual spectra, right? So that's a little bit hard to read if they're all, stacked on top of one another. But yeah, if they spread them out um, a little bit, you're seeing that these stars do have similar spectral features, right? I mean, we're seeing some kind of an emission here from, I guess, helium, helium 2 and carbon 2. But you can see that this emission is about twice as high as this one. So that usually means that there's just more of it, right? There's more of that stuff. But helium 1 here, right? These look about the same or so. So yeah, just kind of interesting looking at, the differences between these. Look at this one. This, I guess this is probably one of the Wolf Rhea stars. Look at all these weird emission lines. And I mean, one has to sort of believe that, they've calibrated out all of the systematic stuff. So, we're not looking at bad data here. All of these bumps, all these things have some kind of a significance, right? So there's these weird little faint, very narrow um, um, emission lines here. So yeah, very interesting. Uh, yeah, cool. Um, Uncle Bill is helping you out. Thank you much, Uncle Bill. But yeah, you can sort of see, the differences between things. I mean, obviously these are the same emission lines, but there looks like there's more of it here and less of it here and about the same and a lot less there. That's kind of cool looking. What else we got in terms of spectra? Hypergiants. Okay, here's some more spectra. Well, here's that pistol star. I forget um, what it said about the pistol star. Um, cluster stars and associated objects such as the Pistol Nebula. Okay, we're not talking about the Pistol Nebula. We're talking about the Pistol Star. P-I Pistol Star. Pistol Star, extremely rare. Okay. Well, let's see. There's a Wikipedia entry for the Pistol Star. Is a blue hypergiant star, one of the most luminous known in the Milky Way. Star owes its name to the shape of the Pistol Nebula, which it eliminates. Okay, cool. So this star is making all the stuff around it right here glow. That's sort of the theory, right? Is that here's the pistol star, and then it's making that that um, starlight is making all this stuff glow. That's pretty cool. I don't think I don't know if my guess is that the pistol star is not in this field of view. That's just my wild guess. Um, Wondering target name. Okay, so this is all the same. This is all the same proposal ID, all observed pretty much on the same day. Wow, they got a lot of data here. That's nice. Is there a position of the pistol star? Because we can use that. Yeah, so 1746 and negative 2850. 1746 and negative 2850. Aha, look at that. That's pretty close. Ooh, these are even closer. Look at that. I'll bet you that's the pistol star. Ah, here we go. Here's more. What, what were these first ones? Yeah, see, these ones were way off. Let's look at, I want to just see an HST image of the pistol star here. 1746, negative 2850. See how close we can get. Here's a 1745, 53, 2850. Let's look at that. I'm not seeing much there. 28. Just dive right into this thing called unknown target. I love those. Okay, so this is like a little composite. Huh, okay. Oh, I don't know. We're not going to have any luck. Not seeing much there. All right. Well, anyway, so yeah, the pistol star. Look at how all these emission lines coming out of that. Helium-1, iron-2, magnesium-2, sodium. Cool. Oh, and yeah, I mean, you can definitely see that there are some differences here. I mean, this line looks like it's even split a little bit. Don't know what's going on there. There's some helium absorption going on here. Do you see how it goes down instead of up? That means that light is being absorbed as opposed to emitted. That's kind of interesting. So much information in these spectra. It's kind of mind boggling. Mind boggling. Helium. Don't you know? I'm gonna have to remind myself what BR gamma is. I'm wanting to say that that's some kind of hydrogen uh, series line, but I'm not familiar with that designation. So lots of helium, lots of helium, a little bit more magnesium there. That's kind of cool. So yeah, they've got some good spectra of all these stars. Pretty cool. Pretty cool. Some more carbon, nitrogen, triply ionized nitrogen, helium again. These are pretty bright stars. I guess these are like the infrared magnitudes though. So you know, I mean, they aren't. None of these stars apparently are visible in at optical wavelengths. You know, so our eyes can't see them. You have to be looking in the infrared in order to see them. So let's see. Are there any other spectra? Oh wow, there's just spectra after spectra after spectra. It's insane. Just looking at a bunch of wiggly lines, you know. But yeah, I mean, there's so much information in all of this. I mean, practically every wiggle here, every um, emission and absorption uh, is telling us something, right? All right, so let's get down to the bottom line here on all these because we can look at spectra. I mean, especially this many uh, for quite a long time. There's the list of all of them. That's very, very cool. It's a much longer list. Makes everybody happy. There's just more data, more and more data. Let's see, identify, blah, 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 blah. Okay. Offer the prospect of advanced single and binary stellar evolution and the formation of both massive stars and star clusters in extreme environments. Very cool. Oh, here's some model spectra. I mean, we got to have our models. Let's see, illustrating the dramatic dependence of bolorimetric luminosity. Blue lines. Yeah, pretty cool. All right, let's get to the bottom line here. So there's a discussion. Let's get to the conclusions. I think there are conclusions. Are there conclusions? Not that there was a conclusion section. Yeah. So this paper reports just information, right? Just lots of data. Um, so the major finding of this analysis is that the quintuplet appears to be far more homogeneous than previous studies have suggested. So not as a diverse um, population of stars as they first thought. Uh, yeah, so they really couldn't figure out the cluster age. But a wild guess, maybe 3 million years. So while the vast majority of cluster members appear um, to have co-evolved, I guess is that term. Um, a few objects challenge that. I like it. 2 to 3 million years. So the combination of the age and mass of the quintuplet present unique opportunities. No other cluster is so richly populated by these massive objects, right? Um, cool. Such stars form via binary interaction. Cool. Haven't yet seen, I mean, I'm still waiting for an observation to be made to actually observe uh, um, these binary star mergers. Doesn't seem to happen. It seems that more likely what happens is that material from one star gets transferred to the other, right? Haven't really seen a lot of mergers. I would think that those would be very energetic events, maybe not lasting long, which is why we're not seeing them. Maybe a merger takes minutes or hours, right? And so you got to be at the right place at the right time to see them. Otherwise, you don't. Uh, Radial velocity spectroscopic survey, what they want to do, model atmosphere analysis, right? They want to be able to put this data into their models in order to hopefully make improvements to their models. Understanding the formation of the coalescing high mass black hole binaries identified. Um, yeah, very cool. Anyway, so yeah, pretty interesting object. Can definitely say that's a lot of this, as I said, is pretty much over my head, but pretty interesting anyway. And yeah, I mean, just a massive amount of work there, just massive, massive. And they got a lot of HST time on this too, which is you know, um, good for them though. The interesting thing though too um, to mention is that that HST data, what is 21 years old now? So yeah, that's another argument for going back to the archives and pulling stuff out because there are jewels there that nobody has found yet, right? And yeah, so that's pretty inspiring. Pretty inspiring. All right, well, I'm going to get out of here. We are way over the hour time, and I am just worn out. So all right, I'm gonna get out of here. Peace, cheers. Um, make sure to hit the thumbs up if you wish, thumbs down if you wish. Make some comments. Share this around. If you haven't subscribed yet, make sure to do so. And I will see you again in a little less than 23 hours. Oh, and by the way, yes, my live stream for June 1st is canceled. I've got a musical gig, and I am going to be away. I'm going to be away, which is extremely rare, extremely rare. But it's going to happen from time to time. Actually, the musical thing is picking up a little bit. Um, uh, yeah, who knows? Who knows? I mean, not picking up in any kind of major way, but do have some gigs lined up already. Got one in July, got one in November. And the November one is potentially multi-day. So I don't know how I'm gonna deal with that. Um, we'll see. We'll deal with it. No problem. All right. Take care, everybody. Thanks for hanging in. I will see you on the spin. See you later. Bye.